Okay.
I found the paper over crystal polymorphisms, specifically in oxyl dihydrazide, sorry, and with asking the question, is empirical DFTD accurate enough? So introduction, crystal polymorphism is when a molecule can form different crystal structures based on certain conditions that are all various degrees of stability. But that's really important for something like pharmaceuticals or semiconductors when they're trying to use some compound in a crystal lattice structure. And when they're very close in energy to each other, they can be very challenging to predict, especially, that's important in computational methods. Energy differences can be as small as 1 kilojoule per mole, which oftentimes is far within range of just variability by basis set and functional choice. A lot of this comes down to intermolecular and non-covalent molecular interactions. So you have like hydrogen bonding occurring within the molecule itself, and then to neighboring molecules also getting hydrogen bonding, plus you have stacking effects. So these can lead to vastly different energy calculations. So crystal structure prediction, we have had some remarkable improvements in recent years due to incorporation largely of quantum mechanical techniques into our crystal modeling. We have improved the quality of our molecular modeling force fields and quantum mechanical based force field parameterizations. Please don't ask me what those are. I don't actually know what those improvements are, but they're there. And then we've applied periodic DFT, that's molecular theory, to molecular crystal problems, often with empirical corrections, which is where this paper comes in. So we've had some very good results in that, but we've also had some bad results. Which leads me to this slide. Standard density functionals are not necessarily reliable for polymorphism discrimination. They're good at modeling when there's only 1 or 2 crystal structures, especially when there's significant energy differences between the two. But when there's very similar energy level crystal structures, it often has a hard time discriminating between which one is the most favorable, and then you'll get different results from different functional uses. DFT often fails to predict, does fail to predict the virtual degeneracy of aspirated polymorphism, as an example. So variations in predictions can be larger than the polymorphic energies involved in the question. Which is bad. Very bad.
Okay, so what's
Which
the
leads
answer?
me to, well, I don't know. See,
we don't know yet.
Well, so that leads us to this particular paper, which is on oxyl dihydrazide, which is that molecule there.
Okay.
How do you go back? Oh, I went back.
Too far.
I didn't realize I hit backwards instead of.
Okay.
Anyways. So, it has 5 experimentally known polymorphs, and 3 of those are very close in energy to each other. And so the calculated energies of each vary wildly with your choice of basis set and functionals. And its difficulty arises from the intermolecular hydrogen bonding and intermolecule interactions. So it has a lot of stacking effects. It's similar to aspirin in that regard, and they have a hard time dealing with that. It has it's alpha, gamma, and epsilon forms are the most stable, but the order is uncertain about which of those is the most stable. All 3 of those undergo an endothermic phase transition to the delta form, to the gamma form at high temperature. Greek. It's Greek to me.
Yeah, it is Greek, huh? All right.
So they know that one's obviously is not also stable. And then the beta form is thought to be the least stable polymorph just because of its structure. So, some methods they did. They optimized the 5 polymorphs starting from the experimental structures using B3, LYP, D, using those 2 basis sets, using crystal and I as a program. For comparison, they also used DPW91 plane wave basis geometries from reference materials to compare. And on all of these geometries, single point counterpoise corrected energies were then computed using a variety of methods.
Okay.
Here's where I'm starting to get over my head a little bit.
Big words in there, huh?
Yeah. And they also used, for comparison, fragment-based hybrid many-body interactions, HMBI, QMMM models to perform second-order multiplicity perturbation theory level, MP2 calculations on the 5 polymorphs. They also performed calculations alongside this with 2 dispersion-corrected MP2 models, the spin component scaled MP2 for molecular interactions, which empirically scales the contributions, and then Hesselman's MP2C, which uses a time-dependent DFT.
Yeah, of course, we'd all think of that, wouldn't we?
Like I said, a little bit over my head here. But
I suspect, though, if you looked all these things up, you learn all about them.
they would make sense, yes.
Some of them you know about MP2 methods, right? Perturbation theory, quantum mechanics, molecular mechanics, all about that stuff, right? So,
yeah.
There you go. Okay, so results.
This is some results from the 5 polymorphisms using the 3 different DFT methodologies on the basis sets. Using those two, using the functionals on the basis sets, and then having the reference functional basis sets. And this is just showing some of their calculated properties, and you can see that there's a large amount of variation between all of them. Well, the first values listed are the experimental values, and then listing is below that is the percent differences by each type of calculation. And you see a lot of variation between them, and it's not consistent variation. You see different variations per everything. Even within the one method, it has different variations per form, which is bad. Very, very bad.
Yeah, that's no good. They must have an answer to that, or they wouldn't get published, right?
Or
no?
Sort of.
Sort of? Okay.
I mean, here they have some, well, yes and no. Here they've got their MP2 results. They said MP2 often overestimates the interactions of delocalized pi electrons in the oxaldehyde backbone, so they corrected for this overestimation using MP2C and the SCS-MI MP2 methods, which I previously mentioned. Right. Finally, they add in the 0-point energy, and that yields results which are very plausible with regard to experimental results.
Okay.
Which is good.
Mm-hmm.
So, analysis. Here is, going back to the DFT methodologies, significant differences in the optimized structure by method, and that leads to significant variations in the computed energy levels of the polymorphs, which leads to a varied calculated order of stability. You don't know, just looking at 2 different sets of results, you don't know what the correct order of the stability of these polymorphs is, so which polymorph is more likely to occur. So the empirical DFT functionals yield results that do not agree with each other or with the experimental data.
Well, that's not good at all.
That's not good at all.
Oh boy.
Yeah, you can see some wild variation in these charts that aren't consistent with each other. So, discussion. Although empirical dispersion-corrected density functionals can perform well for some polymorph predictions, they do appear to struggle in challenging systems such as oxaldehyde or aspirin. This experiment demonstrated that 2 different DFT methods make very different predictions in oxaldehyde, neither of which agree satisfactorily with higher level calculations and experimental results. Conclusions. The best predictions for the polymorph energy ordering based on dispersion-corrected MP2 calculations do agree with the available experimental data, which is good. But in contrast, the lower levels of theory, including the common V3 LYPD and DPW91, dispersion-corrected density functional approximations, fail to reproduce experimental observations and or the high-level calculations. Therefore, better functionals are required for DFT to be reasonably applied towards crystal polymorphisms with close energy levels.
So they just said there's still a problem.
There's a problem, and they need better functionals if they're going to be able to apply DFT to this.
So we're not there yet, huh?
We're not there yet.
Not with DFT. Back to perturbation theory.
That's it. Do we have questions?
Those polymorphs are kind of cool. They kind of remind me of the pseudo-crystal structures, crystals that weren't repeating. So, neat topic, polymorphs, huh? I didn't know aspirin was a polymorph. Yeah. Did you? No. Okay. All right. Well, thank you, Mr. Ball.